So we'll say that we have a small block on a table with some friction connected to a block that hangs from a pulley that's bigger. So we know that block B is going to try to move down and block A is going to try to move to the right. Now A is also connected to the wall with a spring. So what's going to happen is B is going to go down, A is going to go to the right. At some point, they're going to reach the bottom, and then they're going to go back the other direction. Now, if there's friction, then they will stop, then they'll go back the other way, but they won't go back as far because friction is draining energy from the system. Then they'll go again, and then they'll go again. So what it'll look like for them is basically A is going to go out, and then back, but not as far, and then forward, but not as far, and then back, but not as far, like that. And B is going to be basically doing the same thing, down, up, down, up, down, up, down, up. And they will finish out somewhere in the middle. So we need to be given some things in the problem, the masses of the blocks, the friction, and the spring constant and the starting length of the spring. So I'm going to draw this to look a little bit more like a spring there. And we'll say that spring constant is K. And then we have friction down here on the ground or the table, and this friction is mu, and B is not touching and doesn't have any friction. Even if it was touching, there's no normal force between B and the wall. So yeah, it would have slowed down a little bit, but for simplicity, we're going to say that B does not touch the wall and there's no friction there. And we also need the mass of the pulley, because now the pulley counts. And the pulley needs a mass and it needs a radius. And so we need mass for B and we need a mass for A. So let's say that A is 10 kilograms. K is 100 newtons per meter. Mass of the pulley maybe is 2 kilograms. So the pulley is a lot smaller than those. Mass of block B is 15 kilograms. And then the radius of the pulley, oh, and the friction, we need the friction as well. Okay, so let's say here, static friction, actually, we'll just go with mu equals 0.2. I'm not going to differentiate here between static and dynamic friction. We're just going to assume that it's moving and say that is mu d equals 0.2. So just assume that static friction is low enough that the blocks will move. And then we need the radius, and let's see, maybe the radius we'll say is 0.1. Actually, 0.1 meters. All right. So if we're given all that stuff, then we need to find equation of motion for the system. And when the system is released from rest, let's find out what happens. We've got basically a diagram here. Let's put our coordinate frame. And we will say that our coordinate frame starts over here at the wall. And we'll say that X goes to the right and Y goes up. So we've got our coordinate frame, and now we need to write our equations. So part A in Lagrange's method is the potential energy, the kinetic energy, and the L equation. Now, potential energy, the block B is going to be descending, so that's going to lose potential energy. A is only traveling horizontally, so A sees no change in potential energy. And the pulley, which I'll just draw that the pulley is connected out here, the pulley is not going to drop. So the pulley doesn't have any potential energy either. So the only thing that changes potential is B. So we'll say potential energy is negative mass of B times G times Y. distance that B goes down. And then we also have potential energy from the spring. So plus 1/2 kx squared. So we've got that. Now kinetic energy. All three items are going to have kinetic energy. So B and A are going to have translational kinetic energy. The pulley is going to have rotational kinetic energy. So we'll say that we have 1/2 mv squared for the translational, which this will be ma times v for A, which is x dot squared, plus 1/2 mass of B y dot squared. And then the pulley, which is plus 1/2 times I pulley times theta dot squared. Now in this system, we have B, which is going down. We have A, which is going in the x direction. And then we have the pulley, which is turning in theta. But x, theta, and y are all related. So we know that the distance B has traveled is the same distance that A has traveled because they are connected by the same rope. So we know that x equals y, and we'll just call it d for distance traveled. So however far B moves is however far A moves. And then for the pulley, we know that d equals r theta. So now we have related everything, and we can just use one degree of freedom variable, which is d. So we'll say 1 degree of freedom, and we'll call it d, because all of the other motions are related. So we'll go ahead and put that in here. So now we have 1/2 times ma plus mb d dot squared. So we'll say here that x dot equals y dot equals d dot equals r theta dot. Okay, and then plus 1/2 times the pulley moment of inertia, which is 1/2 mp r squared, times the theta dot squared, which theta dot is just d dot over r, and that is squared. So we'll go ahead and cancel. We can cancel this r, which is squared, with that r, which is squared. And then we can rewrite this as 1/2 d dot squared times mass of A plus mass of B plus the pulley has a half and a half. So 1/2 comes out here, and then we'll say 1/2 MP. And you'll remember in our other problem with the hanging bucket, we also had a 1/2 MP, and that whatever the coefficient is of the pulley is basically just going to be the same coefficient for the moment of inertia. So like if you had a sphere, it would be the 2/5. If you have a disk, it's the 1/2. Okay, so do we have everything in here that needs to be? So we have a 1/2, we have a velocity squared, and we have a mass. So we should be good there. So now L equals kinetic energy minus potential energy. And so we'll have L equals 1/2 d dot squared ma plus mb plus 1/2 mp. And then minus the potential energy, which we go minus and then another minus here, mbgy. So that'll be a plus mbg times y, which really is d distance traveled, plus, and that one will have a minus here, and we'll have a plus there. So this is going to be a minus 1/2 k d squared. So now we have everything in terms of d. So part B, we need to take derivatives. So first we'll take position partial. So del L, del D. So we treat everything as a constant except for D, and now D is in two different places here. So del L, del D, we take the derivative of this first one, which we'll just have MB times G, minus the second one, which the 2 and the 1/2 will multiply and cancel, and we'll just say KD. So we can see here that the position derivative, this looks like forces, which it should, because work is the integration of force over distance. And the Lagrange is based on work and energy. So what we had here was energy. We took the position derivative, then we get force. And then we need del L, del D dot. So now D dot is the variable, and we ignore the D stuff. And so here we'll just have the 2 and the 1/2 will multiply, and then we'll just get a D dot times MA plus MB plus MP times 1/2. So at this point, we may as well put some numbers in. So let's say del L del D is massive B times gravity. So 15 times 9.81 minus the K, which is 100, and just times D. And the 15 times 9.81 is 147. And then del L del D is just going to be del L del D is just D dot times MA, which is 10, plus MB, which is 15, plus a half MP, and MP is 2, so half of that is just 1, equals 26 D dot. So now we need to take the time derivative, d dt, just of the velocity. And derivative of d dot with respect to time is d double dot. So part C, we finally put everything together. So we'll need d dt del L del D dot minus del L del D equals, in this case, D is a linear variable, so we will say Fx for external forces. Now, the external forces that we have here are friction. So the friction only acts on block A. And we'll have massive A times G going down. We have the normal force going up, and we have the friction here, and then we have the tension from the rope, which, this is an interesting thing here. Because this pulley has mass, the tension is not necessarily going to be the same in both sides of the rope anymore. So whereas way back with particle kinetics, we could simplify, we said, well, it's the same rope, it's got to have the same tension. That was when we had an ideal pulley with no mass and no friction. Now the pulley is not going to spin unless the tension is different in both sides of the rope, because for the pulley, it's got this tension coming down from block B, and it's got this tension going this way from block A. And if those are the same, then there is no torque on the pulley. So in order for the pulley to move, tension in B has to be greater than tension in A. If it's going to be moving clockwise. And if it's going to be moving counterclockwise, then tension in A has to be greater than tension in B. So really what Lagrange's method saves us from having to do is saves us from having to figure out what are these different tensions in the ropes, because they're not going to be the same anymore. Whereas with Newton's method, if we had to draw a free body diagram for each one, we're going to have to draw a free body diagram for A, for B, and for the pulley, and we're going to have to solve out for tension in A's rope, tension in B's rope, and then substitute all that into each other to finally get one equation. Whereas with Lagrange's, we don't have to know those tensions. We can get the whole equation without knowing them. Because here, we know that the normal force is mass of A times gravity, and the friction is just the coefficient times the normal force. So mu ma g. So that is the external force. So here we'll have, and it's negative because it fights against the motion, negative mu ma times g for the external equals, now we just put in these derivatives that we had before. So d dt del L del d dot is the 26 d double dot. And then we have the minus del L del d, so minus this 147, and then plus 100d. And now we need to go ahead and substitute numbers for the friction. So let's see, what did we say? We said mu d was 0.2. 0.2 times mass of A, which is 10, times gravity, which is 9.81. So that should be close to 20. 19.6. So we have here a negative 19.6 equals 26 d double dot minus 147 plus 100 d. And now we can actually go ahead and move that 147 to the other side. And so if we rearrange that, then we will get 127.4 equals 26 d double dot plus 100 d. So this is our equation of motion for this system. So the equation of motion describes the behavior of the system in response to an input. So in this case, what is the input going to be? Well, it is the force that B pulls with while it's falling, and the external friction force. So as long as B is heavier than the static friction force, which A weighs less than B, so then it has to be, then the blocks will move. But let's look at this in a simulation. I'm going to show y'all the Simulink diagram. So Simulink is made by MATLAB, and you can use it to solve differential equations. So what I put into here, and I did this all with variables because I have this code here where I define all the variables, so I could change these different variables. So massive A, massive B, massive pulley, static friction, dynamic friction, and I put both of these into my model. We didn't calculate here with the static and the dynamic, but I did that. And then gravity, initial spring length, and spring constant. So Simulink operates in the frequency domain, which y'all will learn about once you take feedback controls. But basically this 1 over S means integral. And so when we draw these diagrams, then we feed in. So the mass of A plus mass of B plus 0.5 times mass of P. Oops, where'd it go? Here, okay. So that comes from this part. So mass of A plus mass of B plus 1/2 mass of P. That goes in right here. And this is the time derivative version of it, so it would be times the d double dot. So this point right here on the diagram is acceleration. So we take the acceleration, I'm going to feed that into a graph. Then I integrate that acceleration to get velocity. So that feeds into the graph, but then the velocity is over here, and this is, I find the sign of that velocity. So is it going forward? Is it going backwards? And that affects the way that the friction force points. So we have this mu d times mass of A times g. This is the friction force. And so in this, I'm able to track, is it going positive direction or is it going negative direction? That way it goes in the model correctly. And then finally, we take that velocity and we integrate it to get position. And this position is multiplied by that spring constant here. And then that feeds all back around. And you can see this also feeds to a position graph. And then these are all coming together in this part. And we can see that the massive B comes in here, then the mass, then the friction force comes in here. And the friction force, I have a positive sign here, but remember that the sign right in here is negative. So really it is subtracted. Because B is going to be pulling the weight of B is going to be pulling the blocks forward. The friction is going to be holding it back. So we have that negative. And then the spring is also holding it back. So we've got this negative here. So this is a way to solve a physical differential equation, which is basically a differential equation that represents a physical system in real life. So you can't necessarily solve it by hand, but if you draw the diagram and write the program, then you can. So I'm going to run this and we're going to see what happens to it. Okay, so we can see that the blocks sort of bounce back and forth and then they stopped. Now this graph here shows position, which is black, and we can see that the position does go sinusoidally. So increase, decrease, increase, and then here, it finishes its position at 1.5 and 6. So basically that's telling us that it doesn't end in the same position it started with. And that should make sense because of the friction, it can't go all the way back to the wall. Now the velocity here goes up, goes down, goes up, goes down, and eventually goes to 0, which it should because the blocks are stopped. And then the acceleration, here we can see the acceleration looks a little bit spiky. And this is because of the static friction affecting when the blocks change direction. Some of the energy gets drained from the system, so it doesn't go as far with that dynamic friction. But then because of the static friction, it's extra hard to overcome that. And so we see this jump like that. So we can also change some of the variables and see, like, let's say that we wanted the pulley to be 5 kilograms instead of 2. We can run that and then we can see what happens. And maybe let's say that B is 20 kilograms. So you can see that because B is heavier, it bounces a little bit more. And it plotted those lines on top of the other lines that we had. So we can see that the paths are a little bit different. So we get a bigger position curve here, and this one actually didn't quite stop because you can see that here its velocity is pretty close to -1. So I just didn't run my simulation for enough time for that one to stop. But anyway, so you can see that it's possible to predict the behavior of the system using the equations of motion.